Hello everyone, my name is Hossein, and I'm excited to present our work. FreqDebias, towards generalizable deepfake detection via consistency-driven frequency debiasing. This work was done in collaboration with Nilofer Alipour and Dr. Afka at Clemson University. This work addresses the challenge of generalizing deepfake detectors to unseen forgery attacks. Many recent deepfake detectors perform well on the datasets they're trained on, but struggle to generalize when exposed to new, unseen forgery types. One reason is that their performance drop is related to model bias, where the detector learns shortcuts or spurious patterns instead of actual generalizable forgery cues. These spurious cues can include things like identity information or background textures. But what we found is that there's an additional form of bias that hasn't been studied, something we call spectral bias. We know that different forgery attacks tend to leave behind different artifacts. So, we asked, could our detector be relying on spurious artifacts to make decisions? We analyzed the detector's behavior in the frequency domain. We applied a technique where we systematically removed specific frequency bands from an input and observed how much the classification loss increased. We found that the detector was overly dependent on specific frequencies, which we call dominant frequency components. These are the bands where, if removed, the model performs significantly worse. And here's the issue. These dominant frequencies often vary across different forgery types. So, a model trained on one forgery type ends up memorizing its frequency signature, rather than learning general patterns that transfer across domains. Now that we've seen the problem of spectral bias, let me walk you through our proposed solution. The main idea behind FreqDebias is to mitigate spectral bias and encourage the model to learn features that generalize better across different forgeries. To achieve this, we design a two-part solution. First, we propose forgery mix-up augmentation that enhances the detector's exposure to a diversified frequency spectrum. And second, we propose dual consistency regularization, which explicitly regulates learning across frequency components. Forgery mix-up focuses specifically on the dominant frequency components, the ones the model is overly relying on. Here's how it works. For each forgery image, we transform it into the frequency domain using FFT, separating its amplitude and phase. We then partition the amplitude spectrum into angular segments, and apply k-means clustering to identify important frequency ranges. Using a pre-trained detector, we estimate how much each frequency component contributes to the classification loss. This lets us select the frequency bands that the model is most sensitive to, the dominant ones. Next, we mix these dominant frequency components with those from a different forgery image, while keeping the spatial structure intact. This way, we expose the model to new combinations of forgery artifacts that it hasn't seen before. Second, we introduce dual consistency regularization that works at both the local and global levels. For local consistency, we use class activation maps to make sure that the detector remains focused on the correct spatial regions, even when the frequency patterns change due to augmentation. For global consistency, we move beyond standard feature space modeling. We use the von Mises-Fisher distribution to model features on a unit hypersphere. This allows us to enforce consistency across real and fake images at a more abstract, semantic level, ensuring that the model doesn't drift when exposed to domain shifts. Together, these strategies help the detector break its reliance on dominant frequency components and learn generalizable features. We follow a standard deepfake detection pipeline, using FF++ as our main training dataset and test generalization using 6 benchmark datasets. Let me highlight a few takeaways from our experiments. Compared to state-of-the-art methods, our model achieves SOTA performance in 4 out of 5 datasets under cross-domain settings. We also perform well in cross-manipulation settings. Lastly, we tested robustness against corruption. FreqDebias still holds up, achieving the highest average AUC of 97.6%. To better understand how FreqDebias behaves, let's now look at some visualizations. Figure 1 compares the class activation maps of a standard exception model versus our FreqDebias framework on unseen forgery samples. You can see that exception tends to overfocus on central facial regions. In contrast, FreqDebias adjusts its attention depending on the forgery type. Figure 2 illustrates what forgery mix-up does. For each input, we identify the top 3 dominant frequency components. This augmentation forces the model to encounter new frequency combinations. Figure 3 also illustrates frequency heat maps across forgery types. Let me wrap up with the key takeaways. We identify spectral bias, a hidden form of model bias. We propose FreqDebias, combining forgery mix-up augmentation with dual consistency regularization to mitigate this bias. Our proposed FreqDebias framework achieves state-of-the-art generalization across several datasets.